In this lesson, we're going to talk about the properties of trapezoids. Trapezoids is another type of quadrilateral, but in our previous lessons, we talked about parallelograms and types of parallelograms, such as rectangles, rhombuses, and squares, and they have two pairs of parallel sides. As you can see from the diagram through the middle, a trapezoid only has one pair of parallel sides, and we're also going to talk about something called an isosceles trapezoid as well, and we'll look at some properties of both trapezoids and specifically isosceles trapezoids. But before we continue, I want to fill out this diagram so that way you know the different parts of trapezoids. So the first thing I want to point out is that we have exactly one pair of parallel sides. We call those bases. Now I'm going to label this base 1 like this and base 2. But really, we just call these bases. But just so you can understand, there's the parallel sides of our trapezoid. They are both called bases. It's not just one base like a triangle might have, or other figures. Like it's not just the bottom, right? This one has two bases. On the sides, we call these legs. These are the legs of our trapezoid. And then all of four of those arrows, they're pointing at what's called base angles. They're called base angles. Now, in isosceles trapezoids, there's different relationships that are formed with those base angles that will be a little more specific in the isosceles trapezoid. But let's first look at what that is. Trapezoid with legs that are congruent. So I'm going to draw my congruence markers in here. This is an isosceles trapezoid, similar to an isosceles triangle. When we had our isosceles triangle, we would say that two sides are congruent. And just as an isosceles triangle, when we said two sides were congruent, the base angles were also congruent, the ones right across. In an isosceles trapezoid, the base angles are congruent as well. So I could say this angle and this angle of our base angles, they are congruent. But remember how we have two bases. So the two angles on the bottom here, on the bottom base, are congruent, but so are the two on the top. They're not congruent to each other, like the top one is not congruent to the bottom one, but they do have another pair of angles that are congruent. So the one on the left and the right, left and the right. Let's look at a few theorems. If a quadrilateral is an isosceles trapezoid, so specifically an isosceles trapezoid, then each pair of base angles are congruent. So that's our first theorem. We've kind of already filled that one out from above, but I want to point this out in this theorem that we're going to be able to use just one angle measure to find all the angles. Okay, so in this isosceles trapezoid, trap, RA and TP are what we call the bases. Okay, they're what we call the bases. Therefore, angle T is congruent to angle P, and angle R will be congruent to angle A. And what that looks like as an example is on the right here. Let's look at this first one. I see that this segment is congruent to that one for creating our isosceles trapezoid, which means then since the bottom left base is 77 degrees, angle 1 would also equal 77 degrees. Now, we can use different methods to solve for the two on the top. I do know, based on this theorem, that these two angles are congruent to each other. So we could solve for 2 and 3 in a couple different ways. So one way is I could say the total angle measure of a four-sided figure is 360 degrees. So I could set up an equation where I do 77 plus 77 plus angle 2 plus angle 3 equals 360 degrees. So what I would get is 154, and angle 2 and angle 3, they are equal to each other. So I know, I'm just going to call it x, so you know what those angles would be. There's just two of them, so we're going to write this as 2x. I could do 360 minus 154. And divide by 2, you would get x equals 103, or in this case, each of these angles is 103 degrees. But notice something, right? If those angles actually are 103 degrees, notice how it compares to those bottom base angles. If you were to add 103 degrees and 77 degrees, they would equal 180 degrees. And the reason is because, as we said with our definition of trapezoids, these lines here are parallel. So we can look at it as cut by this transversal. Those are same side interior angles, making them supplementary. So we can do this whole process of finding the missing angle measure with all this algebra, or recognize that they are same side interior angles and that they are supplementary. So watch how quicker I can do the second example without having to do all these previous calculations, but it's really up to you how you solve it. Angle 1 is a base angle, if this actually truly is an isosceles trapezoid, which I can see that doesn't show the segments are congruent, but let's write in our congruence markers. It's not always true. If you don't see the congruence markers, or if you're not told they're isosceles, then we can't just draw this in. But for the sake of our example, I'm telling you these are isosceles. Angle 1 would be 105 degrees, which means angle 2 and angle 3, if this truly is an isosceles trapezoid, that means they are supplementary to those other base angles. So we would say this is 75 degrees and 75 degrees, only if this was an isosceles trapezoid. If a quadrilateral is an isosceles trapezoid, then its diagonals are congruent. So ABCD is an isosceles trapezoid. That means that AC, segment AC, is going to be congruent to BD. This is only true in isosceles trapezoids. If this was just any other trapezoid, it may not be congruent, but with isosceles trapezoids, these diagonals would be congruent. So solve for the length of QS and RP. That means that QS is congruent to RP due to it being an isosceles trapezoid. So QS equals RP. X plus 5 equals 3x plus 3. Okay, so I got x equals 1. But let's make sure that this is correct, right? Just because there's a variable solved for in this problem, we want to make sure that this is actually correct. So I'm going to substitute this back into my problem here. 1 plus 5 would give us 6. And the other one should be congruent as well. We would have 3 times 1, which is 3, plus 3 more, and that will give us 6. So I know that x equals 1 is a good solution. They should be congruent. That was our second theorem of trapezoids. And the third thing we're going to talk about is something called a mid-segment. The word mid-segment. I want you to think of the word middle segment when you hear this. So mid-segment of a trapezoid. I want you to think of this as the middle segment. The middle segment of a trapezoid. It has a very special relationship with trapezoids, right? So this is a segment that joins the midpoints of its legs. Very important there. It has to connect the midpoints of the legs. If you were just to draw any trapezoid and just draw a line through the middle like that, there is no information shown there that makes that a mid-segment. But the second you see congruence markers like those two there and these two, it's telling you that this is the middle point for that left leg and this is the middle point for the right leg. And these legs don't need to be congruent to each other, but the points need to be at the midpoint. So I just want to point that out because it may not be an isosceles trapezoid, but that's not going to matter as long as it connects the midpoints. So here are the relationships that are shown. If a quadrilateral is a trapezoid, and in this case we have a mid-segment, MN will be parallel to RA, and MN is parallel to TP. Remember that the bases of our trapezoid are parallel to each other, so if MN is truly a mid-segment, it will be parallel to those bases as well. The mid-segment, MN, is also going to equal 1/2 the sum of the bases. It's going to equal 1/2 the sum of the bases. Now I find it very helpful, instead of writing it like this, instead of saying the mid-segment is equal to half the sum of the two bases, I sometimes write it like this. Instead of taking half of the right side, I'll double the mid-segment. To equal base 1 plus base 2. It's just a different way of solving this, and it might be easier depending on what you're viewing for a problem. But let's take a look at two examples. This is a base. This is a base. So this is our base 2. And this is our mid-segment. Which means that I can write this as our mid-segment is going to equal 1/2 the sum of 18 plus 36. So our mid-segment will equal 1/2 of 54. So our mid-segment will equal 27. The length of the mid-segment will be 27. What if I had written it a little different? What if I had written it as 2 times the mid-segment? Let's just try that out. Ready? 2 times the mid-segment is equal to 18 plus 36. So let's just try this in a different way. I'll change the color here. 2 times the mid-segment is going to equal 54. You're dividing by 2 anyways in this problem, but even so it's still solving the same problem, still solving for the same length, just looks different. Our mid-segment still equals 27. And another way to check is the mid-segment, the middle segment, is half the sum of the two bases. But I also want to point out, check this out, just a really cool way of checking your problem. Think about what is the length here and compare it to the midsegment. It looks like it is 9 more than the midsegment. Now check out this length here, it's 18. Notice that the midsegment is 9 more than that value. So it's just another way of checking the actual solution. It has to be the same in terms of lengths, the same, how do I say, it's the same distance I get, not that's really the same distance, but almost like it's adding the same value to get to that mid-segment. 18 to 27 is plus 9, plus another 9 more is 36. Just a way to visually check your values is to look at those lengths. But let's take a look at our final example with some algebra. So it shows that MN is the midsegment of the trapezoid. If you're being told it's the midsegment, so that means that M is the midpoint of QP and N is the midpoint of RS. I don't know if this trapezoid is isosceles, but I'm told that MN is the midsegment. So you have a choice. You could either say half the sum of the bases, so I could write this as 2x plus 11 equals 1/2 10 plus 8x minus 12. That's one way of solving it. Or I can say double the midsegment. 2 times 2x plus 11 equals 10 plus 8x minus 12. So I can either add the two bases and take half of it to equal the midsegment, or double the midsegment to equal the sum of the two bases. I actually prefer, in this example, the second one here. That way you're not dealing with fractions. Sometimes you might deal with fractional numbers because of taking the half of the other values. Doesn't happen all the time, but it could. Instead, double the midsegment and it'll come out to the same solution. Okay, so I got a solution. But let's double check. Let's make sure that this is a good solution. If I substitute 6 into that midsegment, 2 times 6 is 12. Right? 2 times, if I put a 6 right here, 2 times 6 is 12, plus 11 is 33. If I substitute 6 into the second equation, I would get 8 times 6 minus 12. So that's 48 minus 12. And that's 36. Did I make a mistake somewhere? I might have made a mistake somewhere. Not 33, it's 23. And this is 36. So in my head, what I did there is I checked my solution because 10 to 23, that's adding 13. So if I add 13 more, I would get to 36. So I made a mistake in this video, and just by quickly looking at the numbers, I can see that I made an error because it should be almost like adding the same values to get to the midsegment and then to get to the next base. So this is a good solution.